So this is a very important theorem in electromagnetics. This theorem states that this theorem is proposed by the Gauss. It states that the volume integral, that means it's a triple integral. So double integral is a surface integral and triple integral is a volume integral. The volume integral of divergence of a vector field. So divergence of the vector field give you a clear idea about whether the field is sinking or sourcing. So three operations we can do with the del, that is the gradient, divergent, and curl. So here the divergence of the vector field. Let us take a vector field A. If the vector A is sinking, we will get a the negative result. If the vector is sourcing, we will get a positive answers. That means, so this is sinking and sourcing. So here we can see that the field is the sourcing from a point. So here the divergent of the vector field is the greater than 0. If it is sinking, if you take the divergence at this point, the divergence of the vector field would be less than 0. So if you get a clear idea about whether the point in the space is sinking or sourcing the vector field. If you take the triple integral of the divergence of vector field, that means the volume integral of divergence of the vector field A, which is over a volume. Here we can see that over a volume some vector field are sinking or sourcing. So this is over a volume. If you take the volume integral of divergence of vector field, which is equal to the surface integral. So surface integral is represented with this surface integral of the normal component of this vector over the surface bounding the volume. Here we can see that there is the surface which is bounding the volume. So there are many vector fields are there. If you take the normal component of the vector to the surface, so let us take that this is A, vector A. The normal component of the vector is, the surface is this one, that is n cap ds, or it can be represented as ds vector. So this is angle theta. If you take the component of the A vector, which is normal to the surface, is vector A dot n cap. A dot n cap. So we can write it down as here the surface integral of A dot. So we can write down in ds form. So this is the divergence theorem. So in this section we are going to see the proof of divergence theorem. So divergence theorem states that the volume integral of the divergence of a vector field. So here comes the volume integral. So here dv is missing. So dv. Because it is a volume integral, is equal to the surface integral of that vector ds. Now what is the proof of this theorem? So we know that the del operator is d by dx of ax ay partial derivative with respect to z and the unit vector az. And let us take the vector ax unit vector, ay the magnitude which is acting along the y-axis and multiplied with the unit vector, and az the component of a vector along z-axis, that is times the unit vector. So all the unit vector gives you an idea about the direction of the the each component vectors. Now if you take the divergence of the vector field, it's a dot product, so we know that Ax dot Ax give you 1, whereas Ax dot Ay equal to 0, and Ax dot Az is 0, and Ay dot Az is also 0. That means you can multiply only these terms together. This will give you a scalar component, that is dou by dou x of Ax plus similarly Ay plus partial derivative of the Az component. Now take the volume integral on both sides. Volume integral of this function, partial derivative of Ax component plus the partial derivative of Ay component plus partial derivative of Az component. Then we need to add, here is missing dv, the volume integral, so this is nothing but dx dy dz, because dv is dx dy dz, this term. Now let us multiply this inside the bracket and take each component one by one. Let us see that the first time the volume integral of partial derivative of Ax component of the vector, that dx dy and dz. So this we can rearrange as, and volume integral of Ax, then dx dy dz. So if you take this term alone, if I integrating that function from upper and lower bound x1 and x2, if you take the partial derivative of Ax terms, you will get some terms, and if you integrate that term with respect to dx, you will get the function in x component. So we can write it down as a vector A x2 minus Ax1. So literally we can simplify this as Ax, because the component which is acting along Ax direction. So this is a simplified version, and if you put it together and if you take it to here, so we can write it down, double integral of this term is Ax and dy dz. So this is nothing but the surface integral. So double integral is surface integral. So this is equal to the surface integral of the Ax component into dsx. dy dz represent dsx. Similarly, the following term also we can write down as such as the volume integral of the partial derivative of Ay component with respect to the volume dx dy dz as surface integral ay and dsy. And the z component, partial derivative of az and dx, dy and dz can be written as surface integral of az ds z. So this term we simplified and we can write it in as, just copying it to the next page. So this is equal to the surface integral of ax term and dsx, the surface integral of ay term dsy, and surface integral of az term dsz. Again we can simplify it as, because ax, ay and az are the component of a vector, so this is surface integral of a vector and ds vector. So now look at the right hand side and left hand side. The volume integral of the divergence of a vector is equal to the surface integral of the component of vector that is normal to the surface which bounds the volume. This is a very important theorem in electromagnetics. So this theorem is very important to convert a volume integral of a divergence of a vector into a surface integral. So for conversion of volume integral to surface integral or vice versa, we can apply this theorem.